Good evening, myself Shaila, and I'll be taking the tutorial classes for powder metallurgy course. So, am I audible? Can anybody confirm that? Am I audible? Okay, so I think we can start. So, I'll be sharing my slides. So basically, for powder metallurgy related course, you might have studied various techniques of fabrication for the powder metallurgy, which involve methods or mechanical methods. In this tutorial, we'll try to cover some of the numericals and some of the concepts in detail related to the powder metallurgy. So first, starting with the fabrication method, like you might have seen that there are different fabrication methods for manufacturing of the powders, and these fabrication methods involve various mechanical milling methods, right? During mechanical crushing, there are different types of forces that will be exerted on the particle. So, for example, we have a powder particle and we wish to crush it, and we can crush it by enforcing various types of forces, which include pressure. Like we will try to act various types of pressures on it so that it can be milled. We can exert a friction force, which will be through these plates on this powder. We can exert an impact force, which will be to push a heavy object against this particle and it will be broken down. Or we have a cutting action or a shearing action, which helps in cutting of the particles to the smaller particle sizes. And now all of these fabrication methods are basically undergo these process steps. For example, while when we are milling a certain powder, we are micro forging it. We are trying to forge it at a minor scale, at a minute scale. Once it is microforged, it gets fractured and there are certain cracks developed in this powder. and these cracks propagate, and as such we are having two different particles of powders. And then there occurs agglomeration and deagglomeration. So these are the general process steps, or these are the general sequence that happens during the fabrication process, which involves majorly the mechanical milling. Now, as you might have seen that you might have undergone various methods of production of the powders, which might include the mechanical combination. It will involve electrolytic deposition, in which you have an electrolytic cell and you have a cathode and an anode. The anode material is being deposited on the cathode, and during that process, the powder will be formed deposited on the cathode material. Another method would be atomization, or there will be some methods based on thermal reduction of the oxides, right? For example, we have Fe2O3, and if you are trying to reduce it in the, say for example, reducing environment such as carbon or carbon monoxide, you can get a powder of iron. So based on different types of methods, we can get different types of shapes, and this is very important in powder metallurgy. For example, if you are going for a chemical deposition method, you will get a particle shape of a acicular type, while if you are going for a mechanical communication combination method, we will have a irregular rod type particles. If you have plate type particles, we can go through mechanical combination because they are irregular type of particles. The electrolytic cell, where you are trying to deposit any powder from the anode onto the cathode, you would always have a dendritic type of a structure. Similarly, if you are having a carbonyl reduction or a precipitation method, the powder shape will be spherical. The atomization will have a irregular type if it is not focused, let's say the dissemination of the stream of the liquid. Otherwise it is mostly rounded if you are doing it in an inert atmosphere, or you are doing in a protective atmosphere. Other shape of the particle is porous if you are going for reduction of oxides, like I said, reduction of iron oxides, or you can have an angular type of shape. So different types of shapes of these powders will influence their properties in compaction. So for example, if you have a spherical type of a particle, then their packing and compaction will be different, the density will be different as compared to the particles which are acicular or irregular type. So this has a great influence on your subsequent processing steps. So it should be remembered that what kind of a method we are using for processing of the powders, and what kind of the shapes are expected from that processes, because that will help in your flowability of the powder, that will help in your compaction, that will also influence your final density of the final product that you are obtaining after say powder metallurgy. So now this is one simple example. This helps us to understand how much increase in the surface area is expected if you are mechanically milling, say for example, a cube. So this is a question where we are taking a cube. It is having a side of 2 units and it has a certain surface area. Now the question is that this cube is being milled. Say for example, it is being milled in a regular shape cubes, and there are about 8 pieces of these cubes, and now they have a surface area of 1 unit. Like each of this cube has a side of 1 unit, right? So you have to calculate what is the percentage increase in the surface area. So you have to just calculate how much surface area has been increased from this one cube of 2 units to these 8 cubes of each of 1 unit. So if you can calculate, it is a very simple numerical. So it is just to understand that how much increase in the surface area is expected after we are milling the substances, or we are trying to approach towards powder metallurgy. So you have to identify what is the percentage increase in the surface area by after milling of a cube of side 2 units to the cubes of sides 1 unit each. We'll try to solve this question where you are asked to calculate the surface area first for this cube. So it will be 6 times the side square. So you will attain a surface area of 24 units for a cube which is having the side of 2 units, right? After milling, if you have 8 surfaces that have been formed, because 8 new cubes that have been formed, the surface area is expected to increase because of there are new created new surfaces. So the new surface area will be 6 times the side square. That will be 6 into 1 into 1, right? Then we have a new surface area which is of 6 units for 1 cube. But there are 8 number of cubes, so the new surface area will be 6 into 8, right? So you have to calculate the percentage increase in the surface area. You can take 1 minute, and if somebody out of you wants to solve it, please let me know. So here we have a increase in the percentage of the surface area by nearly about 100%, right? So we can say that after milling, we are increasing the surface area of all the powders, and because of this, the surface area energy always increases. So the another problem on the same lines is here, which shows that we have a surface area of 2 centimeter. We have a cube of surface of side 2 centimeter, and it is divided into finer powders or finer cubes of each 1 mm side. So you have to identify what are the number of particles that will be produced on crushing of this high larger cube into a smaller cubes. So we'll identify that we'll have the volume will be conserved once we move from this bigger sphere to the smaller sphere, because the volume will not be lost. So based on the conservation of the volume, we have the volume of the larger sphere is equivalent to the volume of the smaller spheres multiplied by the number of the spheres number of the cubes that we have. So the volume of the large cube will be 2 into 2 into 2, because that is the cube, so it will be length into breadth into height, and the volume of the smaller cube is identified from its side, which is 1 mm, so we'll have a volume for a smaller cube also. From here we can calculate what are the number of smaller cubes that are formed after crushing of this large cube, and to get a particle size of 1 mm. So if we are moving from a size of 2 centimeter to a size of 1 mm, we can identify that how many particles can be produced. So here it will be 8 divided by 0.0.1. right? It will be 8 divided by 0.01. There will be two zeros there. So it will give you about how many number of particles will be produced. So it will be 8,000. Now you have to find out how many times has the surface area increased. So you can calculate the surface area for the first cube and the surface area for the second cube. The surface area for the first cube is 6 times the side square, and for the surface area of the second cube is 6 times 1 into 1 into the number of surfaces that are created, number of powders that are created, which are 8,000. Right? And then you can calculate the times the surface area has been increased. The main reason for doing this problem is that you have to identify, or you have to see that for after crushing you always have a larger increase in the surfaces, but this surfaces will result in the large surface energy, right? So if you are crushing a particle from 2 units to 1 unit, you can go to achieve the 1 units for by using certain mechanical milling, but after that it would be difficult to further crush it because there is a large surface area that has been created with a large surface energy, and it is very difficult to further decrease the particle size because of the large surface energy. So when you will be milling any particular material or any powder, you will reach a point where there will be difficult to further mill the powder. So that point is achieved because of the large area, because of the large increase in the surface energy, right? Now we'll move to the another section, which is the crushing section. You might have covered that there are different types of uh, uh, crushing forces that can be achieved for milling of the powders. And in by using this, we are having various types of crushers, which are the hammer, jaw crusher, gyratory crushers, or the ball mill, for example. So basically during crushing, what happens, you have a powder particle, and this powder particle has certain internal defects, and these internal defects in response to the outer forces breaks or propagates first. As the crack propagates, it results in the breakage of this powder, and it results in the disintegration of the powder. So you have to identify, you have to say that crushing is basically the propagation of a certain defect inside the grain, inside the powder, and as the defect propagates, it results in the breakage of this particle. So there will always be certain micro crack, grain boundary defect, or internal phases present in the powder that will propagate on application of the forces, and it will result in formation of the powders. So the powder particles are actually when you are going to crush a brittle material and a metallic material. Say for example, the brittle material, when you are subjecting it to crushing, it will break down into shape of angular form because it is having a tendency to break itself. It has high amounts of defects and high chances to for the energy to transmit. While as for a ductile material, the particles are always in the flaky shapes because in ductile materials or basically the metals, whenever force of crushing is employed on these ductile material, they tend to elongate in one direction because of their inherent ductility property, because they have a tendency to flatten in response to the outer forces. As they are flattened, they result in the formation of flaky substances. So you will not get angular type of particles when you are crushing the metals, but you will always get flaky type of the particles because they have an inherent ductility whenever you are trying to crush the metallic particles. So basically you have seen that there are different types of crushers. One is the jaw crusher. So what is a jaw crusher? Here there is only one movable arm that moves against one fixed arm. So what happens that you put the powder or you put your material that is to be crushed through this opening, and this gate or this flange will try to move to and fro. As it moves, it will try to break the powder that is going through in between the two plates. So it has one fixed plate, one movable plate, and this movable plate will help in crushing of this powder that goes through the gap. Then we have so what we have a jaw crusher in which we have a fixed plate to which against which there is a movable plate moving on, and the powder which is being flown through this gap will get crushed into a powder form. Then we have rotatory crusher in which the central assembly moves while the powder is being put through these gaps at the edges, and as this central assembly moves to and fro, it gyrates, it moves in a circular motion. As it moves in the circular motion, the powder from these edges gets crushed and it is obtained in the crushed form. Then also we have another type of crushing machine which is a roll crusher, in which between the two rolls the powder is getting is put through the two rolls through which the powder is then collected at the bottom. So because of the action of the two rolls, the crushing action at the surface results in formation of the powders. Then we have hammer mill, wherein the process is because of the impact. These types of cutting blades or impacting blades will move while the powder is being put into the chamber. Because of the impact action, the powder is crushed in the form of in this chamber, and you can get a powder of your required size. So you have different types of machines for grinding or crushing, which are jaw crushers, we have rotatory crushers, we have roll crushers, we have hammer mills or the impact mills. So all of these have their inherent principle of crushing based on their different forces. So for example, in jaw crusher there is a compression force. In a hammer mill, there is a impact force. In rolling crusher, there is a combination of compression force, attrition also. So different types of forces are acting on these techniques, and these forces help us to attain the powder of our required dimensions, right? So and also it is important to know that in the powder there are inherent defects, and these inherent defects propagate on application of these forces and results in crushing of the uh, powders. So now this is a jaw crusher. This is a demonstrative lab jaw crusher. I'll play the video for you. You can identify in this video that there is a one static plate against which a moving plate is moved, and that moving plate will help you in crushing of the particles to a powder form. So I'll play the video, and if somebody has any questions, then let me know. So you might have seen that in this there is one movable plate that is moving against a static fixed plate. So this movable plate helps in crushing of the powder that you put through it, and you can get a fine crushed powder uh, at the bottom of the crusher. So this is a jaw crusher in which one plate is only moving and the other plate is static. Now, first talking about ball milling, this is something that is largely done for the manufacturing in the powder metallurgy. The ball milling has certain like parameters that need to be understood. For example, for a ball mill, you need to know what is the ratio of your balls to the mill. Like what is how many balls you are putting in a ratio against your feed material. So, for example, you are crushing certain material A, and how much it is of 10 grams. Now, how much balls you need to put against this 10 grams for those balls to get crushed needs to be identified, because you cannot load the ball mill to its 100% capacity. Ball mill always runs lower at capacities lower than its full capacities. So you have to give some free space inside the ball mill while running it, right? So there is one important parameter in ball milling. It is the ratio of your feed material to the balls, right? Second is how much rotations you are giving to the ball mill. That means rotations per second, or how much milling speed is of the ball mill. So the milling speed will help you to achieve the crushing for your ball materials, right? Then there comes one more thing, that there are presence of certain lifters inside this ball mill. What happens to these lifters? These are horizontal patches or horizontal lines, longitudinal lines inside this ball mill. What they help you in taking is that they lift the feed material, the ball material, or the charge, both the feed and the balls. It helps to lift the charge and carries it to the top, and then lets it come down on its own. So the lifters are helpful in moving the charge material from bottom to the top. So they are just lifting the material. They give you extra energy. They give you extra force for moving these charge material through this ball mill. So in ball milling, you have to identify at what speed you have to operate the ball mill, because for a ball mill there is a speed which is called as critical speed, and that critical speed will determine that how your material will be crushed, or will it not be crushed at all. So you have to identify in ball mill the ball to powder ratio, the ball to charge ratio. You have to identify the speed, the rotations per minute. They have to identify what is the critical speed for your ball mill, and how much charge you have to put in a ball mill, because the ball mill is never charged to 100% of its capacity. It is always charged about 40% about its capacity. So this is a ball mill which is shown here. For this also, I will run the video, and you can identify in this ball mill the rotation of the ball mill. You can identify the lifters that are present inside the ball mill that help you to carry the charge from top to the bottom. And you can identify that with the variation in the speed, the ball milling rotations also change. That means the rotations per minute will change with the change in the like by controlling the ball mill. These longitudinal grooves present on this are the lifters. So, this was the jaw crusher, and this was the ball mill, right? So, can anybody tell me how you identify the two processes, the jaw crusher and the ball milling? Which mill will be which technique or will machine will help you to get more finer powder? Will it be the jaw crusher, or will it be the ball milling? Which is the out of the two processes, if you want to achieve a finer particle size, which is the process that you should adopt? If somebody can tell me, based on how you visualize the two crushing machines. If somebody can uh, tell how are the two processes helpful in achieving the powders? Yes, please. Yes, Swaroop, you can unmute yourself, I think.
Yeah, at the ball mill, because it will have repeated impact, whereas jaw crusher will be once interaction for once only,
Uh,
and whatever extent it can break or it can pulverize, that is only the possibility. Whereas in case of ball mill, it will be depend repeated impact, it will depend on the duration on which we are doing that.
Uh, yes. When you go to a ball milling process, the ball milling process is based that how if you go by the forces that are involved in ball milling, the forces that are involved are that between the two balls there is a abrasion, there is also an impact because the balls will be raised as the ball mill rotates in a circular motion. The balls will be raised to certain height from which it will be dropped. This there will be some impact forces, there will be some abrasion forces that will be acting. So the ball milling is always utilized when you are having already a crushed powder, and that crushed powder it needs to be further reduced in its size. So ball milling is used mostly for like finer crushing, while as jaw crusher, because there is a large gape size, so it is majorly used when you are having crushing from a large lump materials to say coarser size of particles. So for coarse crushing, you can utilize the jaw crusher. For fine crushing, you can utilize the ball mill. But the processing, the forces that will be acting in these two will be different because there are different actions. So now this was the jaw crusher and the ball milling. Now a small identification like what happens during a ball milling process. So in a ball milling process, it is there are three types of motions that can happen in a ball mill. It is cascading, cataracting, and centrifuging, right? So what happens? Ball mill is similar. The ball mill you can think of like uh, picking up the material from here, from bottom of the mill to a top because it is rotating, and then dropping it off. It is similar to how your washing machine works, right? In your washing machine also this similar principle is applied. It is just that the balls from inside the material here, they are the balls. This ball mill, when they are inside this ball mill, there is a charge and there are balls. This charge and balls will try to move upwards as the ball moves. As the ball mill moves, this charge and charge consisting of the feed material and the balls will move to the top, and then it will fall down. So if you try to get it in a very fast motion, for example, you give it a very large speed, you will see that all of the charge will be sticking to the balls. This is how a classical example what happens in your washing machine, that all of your charge material gets sticks to the wall. But in ball milling, this is not desirable. Why? Because we want the crushing action in the ball mill. We want the charge to be broken down with the help of balls. So for that, we need to have a certain impact force acting inside the mill. So what we have a centrifuging force. The centrifuging force is the most undesirable phenomenon for the ball mill because this is occurring at very high speeds. All of your charge material will be stuck to the walls and it will not result in any impact action or any forces for crushing of your material, right? But there is another method which is the cascading. That means if you run the mill at a very slow speed, so what happens? The material just swings. It just goes to certain height and then comes back. So there is just a swinging action for the ball, for the between the ball and the material, and there is no impact or crushing force acting on the mill. Because of this, as a result, what happens? The material is not crushed. The maximum that you can expect in this process is that there are abrasive forces acting, but there's no impact force inside the mill in the cascading mode. But when it is the cataracting mode is the most desirable phenomenon where the charge material is raised to a certain height. It is not even raised to a total like 180-degree. It is raised to just less than 180-degree, and from there it is just drops down in a circular form to the bottom of the mill. So this helps in crushing of the material whichever was present at the bottom because of the impact, also because of the abrasion and the attrition between the balls and the feed material, the crushing happens. So the most desirable phenomenon in a ball milling is the cataracting, while cascading occurs when there is a very slow speed, and this slow speed only helps you to swing the material in the ball mill, but does not help you to crush the material. While in centrifuging, that is a at very large speeds when you are running the ball mill, the material sticks to the walls and you are not able to crush the material at all, right? So whenever we see this, this represents that there is always certain speed at which the ball mill should be run, and that speed is called the critical speed. So you have to maintain a certain speed at which the ball mill will have a maximum efficiency for its crushing. Okay, so that speed is called as critical speed. We'll do a numerical on that. So first, these are the, like, to identify the motions of the grinding media. We saw that these, when it is just swinging along the walls, it is happening just shearing. There is no action or of impact. There is no crushing action. While if it goes to top and then comes down, it is called as cataracting. And it, as it falls at the bottom, then it creates an impact zone which is called as a toe. That means the balls and the charge rises here, and then it falls at a point which is called as toe, and the major grinding happens in this region, while there occurs no grinding in between this region. The major grinding only occurs along the edges and along this path at which it drops near the toe. So you need to identify that for a ball mill you have to keep it not filled, because you have to achieve this open area for milling purpose. You have to have some free space inside the mill for crushing purpose. So in order to calculate the critical speed for a ball mill, there is a formula. It is given by 1 by 2 pi under root of g. G is the acceleration due to gravity, and r, capital R minus small r. So this capital R represents the radius of the mill, that is this complete mill. The radius of this mill will be represented by a capital R, while the radius of a balls, that are the grinding media that is used inside this, is represented by R. So you can see that the critical speed is highly dependent on two factors. One is the radius of your mill or the diameter of your mill. That means how big is your mill. So it will depend on that. The other factor is the diameter or the radius of your balls. So these are the two factors influencing your critical speed and thus influencing the crushing or the impact action ball, inside the ball mill. So you need to identify that this is the critical speed for a ball mill. Now, there's a question. The question is, are brittle materials more responsible for milling, or metals are more responsible for milling operations? So what is your opinion that if you are going for a crushing action or a milling action for a brittle material and for a metallic material, so which will have more response? Out of the metals and the brittle materials which are present, which is having a better response towards milling? Because the purpose of milling is to crush or break down the material. So which will have a better response, the brittle material or a metallic material? Anybody? So basically what we see is that for a brittle material, it is having a tendency to break because of high defect positions. Because it is a brittle material, it will have a higher response towards crushing. But for a metals, we have an inherent ductility present in them, and that inherent ductility will not make them be milled as easily as the brittle material will be, because simply they have a tendency to be ductile. They have a tendency to have a property that they flatten out, they form flaky substances rather than breaking into two pieces, right? So the brittle material will always have a higher response for milling because it will easily break down, while for metals the response will be slow because it will tend to first flatten out, then the flattening of the material will help in cold welding of the two metals, and then we can think of production of the powders or production of the components from powder metallurgy. So overall the response of the brittle materials is much higher as compared to the response of the metals towards milling. So you can see this in this diagram where you can see that this is the typical process for a brittle material. The brittle material in contact with the two surfaces will break down into pieces, while the ductile material, which are basically the metals, will try to elongate as the compression force is applied or as any kind of force is applied on the metals. So it will try to flow out or it will try to elongate in one direction because of the inherent ductile property. So for a brittle material, when we are talking the brittle material, it is given the fracture strength or the impact strength is given by the formula where sigma is the impact stress and it is given by 2 ER, where E is the elastic modulus, R is the radius of the crack tip, because it is there is always a certain defect occurring inside the material that will propagate, and that is depending the stress impact will largely depend on your radius of your defect, and it will also depend on the particle size. So what we understand from this equation is if you are given two particles, one particle is say of 500 micrometer, one particle is of size 1 micrometer. So which is the out of the two particles will have a higher impact strength? Like which particle will need a higher impact stress as compared to other particle? So one particle is of 500, I'll write it here. So I have two particles, one is 500 micron and one is 1 micron. So out of these two particles, which particle do you expect to have a higher impact stress? Once you are trying to form a powder mill it or you are trying to mill it, which size of the particle will have higher impact stress? Yes, yes, Varun.
Yeah, it's the finer particles have higher impact. Require higher impact.
Yes, the higher impact stress. Now you can relate it to the surface energy problem that you did. You have you have a smaller particle size, it has higher surface energies. Higher surface energies will result in higher impact stresses. Also this is very important to understand in our milling process, like how far we can go to milling. For example, if you are you are given a mill and you are asked to mill a substance, say for example to 1 mm, you are able to mill the substance to 1 mm, then you are asked to mill the same substance to now 100 nanometer or 100 micrometer, but you won't be able to reach to that length or that position because the prolonged milling or the milling for larger times does not have any influence on crushing, does not have a significant influence on getting to a smaller size, because as you are going towards a smaller size, the surface energy is increased, it will be much difficult for the particle to crush further, so to be crushed to a further size, so it will be always difficult to get finer size particles because they will require higher impact stresses. So you need to identify that it is not that you will infinitely go to milling the particle and you can achieve nano size or a micron level size. You need to identify that up to what particle size you can achieve in a particular mill or in a particular process, and how much energy will be required, because there will be huge amount of energy required for milling a milling up to a finer material as compared to a coarser material. So in powder metallurgy, apart from the technique of milling, it is very important to identify that what is the particle size, because that will influence the amount of energy that you will exhibit in the process. It is important to identify how much is the particle, what is the particle shape, because that will influence your subsequent processes, which is the compaction, which is like sintering, so density of the material. So apart from the processing of milling, we also have to identify the various influences of the particle sizes and the particle shapes. So if you can see, this is a ductile material. This is a micrograph. It's a micrograph which where we see the particle shapes of the material. It has been milled, and after milling, you can see that the material has flattened out because of the milling. The flattening of the material is because it is a ductile material. Also, what happens that the two particles try to cold weld with one another. What happens, there are small places of high energies that are created between the two particles, and which have because of that there occurs a localized melting or localized welding between the two particles, and as such the particle size increases for the ductile materials instead of a brittle material where you have a particle size going down always. For a ductile material, because of the inherent ductility, the material flattens out. There is a cold welding between the two particles, because of which the particle size might increase. So this is the difference between the milling response for a particles of ductile and the brittle material. So this is an example. So for this, in this question, we are taking a ball mill of 2 m diameter. So this is a ball mill having its diameter 2 m, and it is loaded with the steel balls, each having a diameter of 4 centimeter. So here you can see in this numerical that you need to charge the ball mill with certain material with balls, and these balls can be either steel balls, they can be tungsten carbide balls based on the material that you are milling. So if you are milling a very hard material, then you need a harder balls in the harder ball mill. But if you are milling a softer materials, it can be milled with the help of steel balls only. So we have a ball mill of diameter 2 meters. We have a steel balls with a diameter of 4 centimeter, which are loaded in the ball mill, and the rotational speed of the ball is kept 70% of the critical speed. So you have to calculate the operational speed of the ball mill. So first, in this question, you have to calculate the critical speed. After that, you have to calculate what is the operational speed of the ball mill in rotations per minute. So you can take 5 minutes to solve, then I'll also solve it. So you can take 5 minutes for solving it. So, if you have anybody has solved the problem? Yes. Has anybody solved the problem?
It's around 0.35 RPM.
0.53 RPM. So first I'll just go. Are you sure it's 0.53 RPM? Because remember that we are doing this 9.8 into 2, 2 into 2 is the mill diameter. So first I'll just write here. So basically what we are trying to do, we are calculating the critical speed using the given data. So we are given that the diameter of the mill, that is 2m, which is the capital R in the formula. Then we are given the diameter of the balls, right? The diameter of the ball is 4 centimeter, which we have converted to meter, and it is now 0.04 meter. Is it right? So now we have put the values in the equation, which is NC is equal to 1 by 2 pi under root of G R minus R. So remember G is the small g is equal to 9.8 meter per second square, right? So whatever the answer you will be getting here after putting the values, it will be in RPS, that is rotations per second, because we are taking 9.8 meter per second square. The units of G are meter per second square. So the overall units will be in rotations per second and not in rotations per minute. Is it clear? So you will be getting the critical speed as 0.503 rotations per second. So now if we calculate it to be in meter, so for 1 second, the number of rotations are zero point 0.5, right? But for a minute, that is for 60 seconds, the rotations will be 0.503 into 60. That will be rotations per minute, right? So this is a critical speed for a ball mill. This is just the speed at which it should be operated so that the crushing action will be done on the ball mill. So it will be around, I think, it will be 30 RPM. I think so. But we are operating it at a 70% efficiency. So 70% of the critical speed. So that will be zero point 0.3 into 0.7. So that will be your operational speed of the ball mill. In this problem, you have to remember that the units of this critical speed are not the rotations RPM, but they are in RPS, that is rotations per second. And after you are converting it, you are getting the rotations per minute. So if anybody has any doubt or any question, anybody has any doubt or any question? So I think we can move to the next problem. So the next problem is that for a metallic chips of initial size 500 mm. So you have a chips which are of metallic chips and they are of size 500 mm, and after they are machined, they are milled to a powder size of 100 mm. So the milling process, the machining process will result in the converting of the particle sizes of 500 mm to 100 mm. So this is the step one. And this process, that is the conversion of the metallic chips from 500 mm to 100 mm, requires a time period of 10 hours. Okay, this is the amount of time that is required for milling of the metallic chips from 500 mm to 100 mm. Now you have to calculate what is the additional time that is required for milling up to the size of 38 mm. So this is basically a problem in which you have to go for a relative. So how the you have to take the first process in which from 500 mm you are milling to a 100 mm size, and it takes 10 hours. Now you have to identify if you mill from a 10 mm size to a 38 mm size. So how much time will it take, right? So you have to take the formula which is used for calculating the energy during this milling process, which is given by G dF minus di. These are raised to power minus a. These are some empirical constants. And the dF is the final particle size, di is the initial particle size, right? And a are the empirical constants. So you can take a here, let's say 2, because it varies between 1 and 2. So the empirical constant you can take here as 2. The value of a here is 2. Okay. So you have to calculate what is the energy required for milling in the second step in relative to the process that is carried in step 1. So you have two-step process. So you can try the equation, then I'll solve it with you. Based on the relative milling times, you can calculate the milling time required for the second process. So you can take 2 minutes and you can try to solve it. After that, I'll solve it. So what we have in this question is that, so we are basically having in first step, we are milling from 500 mm to 100 mm in 10 hours. In second step, we are milling from 100 mm to 38 mm in say x hours. Okay, so what is the energy that is required, say for example in step 1? So we can say it is g times the final diameter, which is the final diameter here, that is 100. That is 100 raised to power minus 2, because we are taking the empirical value as minus 2, then minus the final diameter, that is 500 raised to power minus 2. Is it clear? So this is the energy required for the step 1. Then we have step 2. This for step 2 we have energy equivalent to the final diameter, which is 38 raised to power minus 2 minus the the initial diameter, which is 100 raised to power minus 2. So what will you try to do? You try to find W1 by W2. So that will be equal to, what will be the ratio between W1 to W2, if somebody can calculate? I think, can somebody tell me what is the ratio between W1 to W2? You just have to divide the two equations.
Point 0.62 maybe total.
Uh, 0.62, like it is the time required. 0.62 is the ratio between the two. I think it is
Time required.
time required, but okay, let us first do the W1 by W2. So I think it will be, let me see what it is. It is 9.6. Okay, I think W1 by W2 will be 0.162, right? So that means there is, for the energy required in the first step is 0.162 times the second step. So W2 by W1 you will find out, that will be 1 divided by 0.162, that will be 6.17. 6.17. So that means that the energy required in the second step will be 6.17 times the energy required in the first step, and the time will be also in relation to that, that it will be 6.17 times the required in the first step, that is 10 hours. So that will be equal to 61 hours. Is it clear? So you can say that the amount of time that is required for milling from 500 to 100 mm, it is just like uh, 5 times a greater size. So you are trying to get to only 10 hours, but if you are trying to achieve to 38 mm, which is about 2 times, so you are having a time required about 61 hours. So the time required for milling to a finer size will be much higher, because you are trying to work against the impact stresses, you are trying to work against the large surface areas. There will always be large amounts of energy required to mill to a finer size as compared to the energy that is required to mill in a coarser size fractions. So this problem helps us to understand that the time required for a finer size fraction will be much greater than the time required for crushing in a coarser size fractions. Okay, so in this context, there is one graphical chart here. in this graphical chart, I want you to understand that if we have a energy versus size of the powder graph, and you have to attend like this, we did this just now, that the particle size which will have a higher energy. So we understood that the lower particle size will have a larger impact stresses. Now we have to plot between the energy of requirement for crushing, for formation of the powders, for milling of the powders, and the size of the powders. Say, and we have to place these crushers and mills up at appropriate places in this energy versus size graph, right? So first, I'll just put a scale for the size of the powder. So for example, this is 1 micron meter, 1 units. For example, we will not define the units. We'll go for the 1 units. We'll say 10 unit. We'll say 100 units, like that. So this is the size of the powders. So you can see as the powder size increases, and here is the energy. So you can put energy in the form of, say for example, kilowatt hour per ton maybe, right? So what is the where appropriately should we place these mills or these crushers in this energy versus size of the powder? Say for example, if I go for the jaw crusher, I know that for a jaw crusher, I will have a larger particle size. I'll have a coarser particle size. So the energy required will be comparatively lower as compared to, say, for other mill type. So the jaw crusher, I'll place it somewhere here that the energy is significant, but it is a larger particle size. Just a random positioning of these mills, but just to understand the relationship between the particle sizes and the energy gets to understand, and based on the mills, what appropriate mill should we utilize. So for example, now we talk about impact mill. So where can we put this impact mill appropriately? I think it can have a slightly better energy requirements, but you can have a smaller particle sizes achieved in this mill. So if you go for a jaw crusher, you will have a larger particle size, but the energy required is decent. Then if you go for an impact mill, the energy requirements will be a little higher because you are going towards a smaller size particle. Similarly, if you have a ball mill, for example, or a rod mill. For a rod mill, you have a slightly bigger size as compared to ball mill, so it will be somewhere here. For a ball mill, you have a smaller size fractions, but the energy required will be higher. And for a iterator mill, the energy will be much higher, somewhere here. So based on this, what you understand? You understand that you have a relation. There's a significant relationship between an energy that is required for crushing of the powder. Simply, if you have a smaller particle size, you have a high amount of energy requirement. This will be graph like this, from top to the bottom. If you have a coarser particle size, the energy requirement will be less. Then how are we classifying different types of mills? We are classifying the different types of mills based on their energy products, and based on their product in the terms of size of the powder, and based on the energy required to achieve the said powder size. So you can have such type of this is just a general representation of how we can do. We can say that this is the order for crushing. For example, if you have a very large particle size powder, you can first jaw crush it, then you can go to impact milling or ball milling it. So we do the stepwise crushing also to have a different size distribution of the particles. So this gives an idea that apart from the particles size and shape, we are also concerned with the energy required for crushing of the powders. So that energy has a significant influence on our powder produced. Now there is one more question. This question is based on the time required for the grinding. So we have a mill, and that mill is operated at a speed of 2400 rpm. So this was a rotations per minute. So you are having certain speed, and that is used for crushing to a size less than 1 mm for 30 minutes. So you are running a mill for 2400 rpm for 30 minutes to crush to a size of, say, less than 1 mm, and you have to operate the same mill, same conditions, for 20 minutes only. You want to operate it for a smaller duration of the time. So what should be the speed of the mill? So based on the time of the grinding, you can calculate the speed of the mill at 20 minutes. we can do this numerical, then I'll solve it with you. You can take 2 minutes for solving. So has anybody solved it? Has anybody attempted the question? Okay, we'll try to do it here. So here we are saying that we are operating a mill at a speed of 2400. So say for example N1, that is equal to 2400 RPM. Okay, and we are saying it is operating at a time for a time period of 30 minutes. So 2400 for 30 minutes. Now keeping the conditions, rest of the conditions same, because here the time of the grinding is dependent on CD square. The D is the grinding media. So we are not changing the grinding media. We are keeping the mill same. We are just changing the speed of the mill. So we have to identify what is N2, right? And we have to see what is the time. Time is 20 minutes, right? So if we go for T1 by T2, T1 by T2, that will be equal to 30 by 20, that will be equal to 3 by 2, that will be equal to 1.5, right? Then we'll have n2 by n1. N2 by n1 will be equal to, because n2 we do not know, by 2400, right? So it will be 1.5 into 1.5, that will be equal to N2 by 2400. So that will be equal to 1.5 into 1.5 into 2400 equal to N2. So that will be the speed of the mill. So what will be the speed of the mill? Can anybody calculate? I think it will be 5400 RPM. So what do you understand? You understand that if you are decreasing the time for operation of the mill from 30 minutes, you went to 20 minutes. You have to increase the speed of the mill to achieve the crushing at the same for the same size, right? So the time and the rotational speed, the time of milling and the speed of the mill are related. They're inversely related by the square root of the speed. So for if you try to decrease the time of milling, you have to increase the speed, or if you increase the speed, then you can decrease the milling time. So the milling time and the speed of the mill are also related, right? Any question, any doubt? Okay, so this is one more question. This is based on the thermal treatment of the powders. Like you have read this up till now, we read about that there are different types of mechanical methods of milling, and there are different machines that are related to it. There are different shapes and sizes of the particles that can be obtained based on the type of processing that we do. We have the relationship for the critical speed. We have a relationship for energy of milling based on the particle size. We have the relation for the time of grinding. So all of this was based on the mechanical milling of the processing of the powder milling, right? Now what we have the for processing of the powder, we can also use the gas based reductions, right? So for example, here there is an one of the reaction. It is given that nickel oxide, right? Nickel oxide is forming with the help of H2O. You can reduce the nickel oxide with the help of H2, hydrogen gas, and you can form a nickel metal and a water. So this is one of the methods of production of the powders. Also for chromium powders, from chromium oxide, you can purge hydrogen gas and you can reduce the chromium oxide to chromium and H2O, right? So these are the two characteristic equations for the reduction of the nickel oxide powders to nickel. But also this is important, this can be also read vice versa. Like for example, you have produced by some method a nickel powders, and those nickel powders in presence of moisture or in presence of water, they can oxidize back to nickel oxide. Similarly, chromium in presence of moisture and hydrogen, they can oxidize back to chromium oxide, which is undesirable phenomenon for a powder metallurgy, or even desirable. But here we need to understand that these equations can be read as the reduction reactions, because we have nickel oxide reducing to nickel and we have chromium oxide reducing with the help of hydrogen to chromium. Or we can say in presence of moisture, the nickel or the chromium can be converted to their respective oxides, right? So this is one of the methods of producing powder metallurgy. Sorry, in the method of producing powders using reduction, gas solid based reductions, where the gaseous medium is reducing your reducing your powders, oxide powders, to their metallic forms. Okay, so we have a question here that we is given the following data, determine which metal has greater probability of, this is probability, which metal has a greater probability of oxidation in presence of steam at 827 degrees Celsius and 1 atmosphere. So the question asks that if you are producing the two powders, say for example nickel and chromium, and in presence of some steam, which is H2O, you are producing nickel oxide or chromium oxide back. That is, you're oxidizing the metal powders. So which of these two metal powders which have been produced by you and in presence of steam, they will be converted to their oxides. So you are given two equations. You are given their delta G, which is the Gibbs free energy values, and these Gibbs free energy values, and you are given the temperature, right? So the temperature is at 827 degrees Celsius. So you have to solve these equations. So how will you solve it? The reaction which will have a lower Gibbs free energy will be oxidized more, right? Based on the equation that you write, the negative Gibbs free energy means the reaction is more feasible. The reaction will occur more, is more favorable than the other reaction. So based on the Gibbs free energy value, you can determine which of the oxides will be formed first, or which of the oxides' formation is more favorable. So you can take 5 minutes for this, but you have to remember that you have to take the oxidation reactions, because you are talking about the probability of oxidation. So this is the reduction reaction, this is not the oxidation reaction. So you have to reverse the reaction. You have to write nickel plus H2O gives nickel oxide plus H2, and chromium plus H2O gives chromium oxide plus H2. So these are the reduction reaction, these are the oxidation reactions. So you have to write the two oxidation reactions, and because you have reversed the reaction order, you have to reverse the delta G values also. That will be delta G naught for this reaction will be negative of what it was for this reaction, and also for this it will be negative. So you have to find the delta G for the two reactions. So you can take 5 minutes and solve it. Then we'll solve it. You have to find the delta G value for the both reactions. I'll write here the delta G for nickel oxidation. That is, the delta G for production of 1 mole of nickel oxide is equal to negative of minus 2301 minus 42.59. That is what it was for the reduction reaction, the negative of that, right? 42.59 T, that will be equal to negative of minus 2301 minus 42.59 into, what is the temperature? Temperature is 1100 Kelvin. So this will be the delta G for the nickel oxidation. But you have to also see that for delta G of chromium, because we are oxidizing chromium, we have to we can compare the two equations only when we are talking about 1 mole for each. That is, this is the production for 1 mole of nickel oxide, but this is not for 1 mole of chromium oxide. So you have to make sure that you convert this equation. So how will you do it? You have to multiply it by 3. So now the new equation that you will have, you have 2 times chromium, 3 times H2O, 1 times chromium oxide, and 3 times H2. This multiplication of 3 is done so that we have 1 mole of chromium oxide and 1 mole of nickel oxide. So now we can write the delta G for chromium, that is the chromium oxidation, that is equal to negative of negative 3 times 126,566 minus 30.67 times the temperature, that is 1100. So can you calculate the delta G for the two equations? In this problem, there were two things that you had to note. First, that the we have to compare the probability of oxidation. So you have to form the oxidation reactions first. So for that, the delta G values will change accordingly. Second, you have to find for 1 mole of the two species that because you're comparing, you have to have 1 mole for both. That is 1 mole of nickel oxide and 1 mole of chromium oxide. So for that, the delta G values change slightly, and as the delta G value change, the final value for nickel and chromium oxide oxidations are given. So what is the answer for the delta G for nickel oxidation? I think it is 49.15 kilojoules. Okay, and for chromium, it is negative of 278.4 kilojoules. So which oxide will be formed first, which has a greater probability of oxidation? Can anybody tell based on the delta G value? Based on the delta G value, can you tell me which is the more prone to oxidation? Is it chromium or is it nickel oxide? Nickel. Okay, so it is chromium because we have a negative delta G value for chromium. It will be more prone to oxidation. Now we have some MCQs. I want you to attempt these MCQs and like answer accordingly. So one first MCQ is what is the maximum size a powder part? This is based on your this week's classes. So the MCQ is what is the maximum size of powder particle can be? Is it 1 nanometer, 100 nanometer, 1 millimeter, 1 micrometer? Which of these will you define to be a powder?
1 millimeter.
1 millimeter, okay. For next question is the powder metallurgy techniques are suitable for metals and alloys, ceramics, polymers, and none of the above. So, powder metallurgy is used for which of the following? You have read about powder metallurgy techniques being used. So, for which of these are the powder metallurgy techniques used?
Both A and B.
Yes, they are used for metals and alloys, and they can also be used for ceramic materials like silica, alumina, yttrium oxide, zirconium oxide, something like that can also be used for powder metallurgy. While polymers cannot be because we are trying to process it into a finer powder size. Now, next question is which of the following is not a characteristic feature of a metal powder? Okay, high surface area, flowability like a fluid, compressibility like a gas, none of the above. So you have to say that which is not a characteristic for a metal powder. You have a metal and you have its powder. So which of
None of the above. None of the above.
do you think that it has a high surface area in comparison to say for example ceramic or a brittle material? Because we read that the metal powders have a tendency to cold weld. So as they cold weld, they will result in higher surface, the higher like joining of the surfaces, and there will not be high surface areas. The surface area will be decreased during the cold welding process for the metal powders. So the high surface area is not really a characteristic for a metal powder. So the answer is high surface area. Okay.
But I series surface area may be required in the next stage, that is sintering.
Yes, in sintering you require, but when you compare it, because we are comparing it with a metal powder and a ceramic powders, like if you see a metal powder, it has a tendency to cold weld, it has a tendency to form metal bonds, so it will have a comparatively a lower surface area, right? So we can go to the next question. The advantage of using powder processing technique includes the working temperature is well below the melting point of the material. The chemical compositions which cannot be processed by conventional routes could be processed using powder metallurgy. Enhanced reaction kinetics because of the higher specific surface area, or all of the above. Can you tell me what are the advantages of using powder processing techniques?
All of the above.
Right, it's right. But say, for example, we are saying the working temperature is well below the melting point. Can you name any metal for which we are doing powder metallurgy and the working temperature is well below its melting point? A very classical example for such powder metallurgy processes. Any example where you know that the working temperature is very less as compared to, say, the melting temperature. That is why we are not going for the casting, we are going for powder metallurgy.
Maybe lead, something like that.
Mm, Not really. Lead has a melting point about 250 to 30, something like that. For example, tungsten. The tungsten has a very high melting point. So that melting point, that's why we never use it for cast. Don't go through the casting method. We go through powder metallurgy route for processing of tungsten powders. Then the answer is right. The answer is the all of the above. And we have another question here. Which of the following products are best produced using powder metallurgy? Brake pads, cylindrical piston heads, crankshafts, none of the above.
Brake pads.
Yes, brake pads are produced by powder metallurgy, while crankshafts are sometimes also produced by casting routes. So, which of the following uses powder metallurgy techniques? Furniture, kitchen utensils, mobile phone panels, pharmaceutical tablets.
Pharmaceutical tablets.
Pharmaceutical tablets, right? Because we are taking a powder form, then we are pelletizing it, we are taking pelletizing and then forming it in the form of tablets. While for other applications, we are using the properties of malleability and ductility to, say, for example, form the utensils or mobile phone panels or even furniture. So, next question is which of the following will have a better packaging inside a cylindrical glass? Spheres of 10 mm dia, cubes of side 10 mm, a mixture containing equal numbers of spheres of 10 mm and 5 mm dia, both A and C. Simple packaging problem.
C, maybe C.
Yeah, it could be C because the better packaging will be if the whites between the spheres are also accommodated by some other particles of lower dimensions. So you can fill the cylindrical glass with 10 mm dia spheres, and then the whites between the spheres can be filled with say smaller particle, smaller diameter spheres. Next question is which of the following is not a mechanical method of powder synthesis? Attrition, shearing, hydrothermal method, high energy milling.
Hydrothermal.
Right, hydrothermal. Do you know what is hydrothermal method? Any idea what is the hydrothermal method? Because like attrition is simply the rubbing action of the between the particles, so it is a mechanical method. Shearing is cutting between the two particles. It is mechanical. The high energy milling is itself milling. High like milling process, a mechanical process. So hydrothermal method. What is the hydrothermal method? Uh, in a hydrothermal method, what we have a vessel, reaction vessel, which is a high temperature, high reactor vessel, high temperature, high pressure reactor. We have a high pressure, high reactor vessel. Okay, somebody wants to join. So, like for a hydrothermal method, what we have a high temperature, high pressure reactor. So, you take the powder. For example, if you have a copper is dissolved in your solution. So, for example, copper sulfate solution. You have a solution, you have copper ions in it. You take this in a hydrothermal vessel, in a vessel which is having high temperature and high pressure conditions. So, you have hydro conditions, you have thermal conditions. So, because of those conditions, you can precipitate out or you can extract out some of the desired metal ion. So, for example, copper. So, you can precipitate out the copper from the solution at high temperature using hydro like aqueous medium, So you can have a powders of copper, so for example. So this is a hydrothermal method. The hydrothermal method needs high temperature, high pressure requirements. So you can extract certain metal ions from the solution. So it is not a mechanical method. It is just a combination of a hydrometallurgy and a thermal method. Next question is milling results in A. Mechanical alloying, B. Changes the property of the materials, C. Changes in particle morphology, uh, fourth, cold welding of the particle. So there are some combinations of the options. So you can pick up one. You can say that milling will result in which type of a combination. Any answers?
1, 2, 3.
One, two, and
3.
one or four.
1, 2, and 3 will correct.
But four will also happen if you are talking about the metallic species. Mechanical alloying also occurs when you have one metal and one non-metal, maybe compositing formation of. So you can say in general, because this is not mentioned, so you can say all four of the options are correct, because mechanical alloying can also happen in milling. There is properties of the material also, because you have different shapes of the powders formed. They will have effect on their density and their flowability and their packaging characteristics. The morphology changes, and also there occurs a cold welding of the particles if they are the metallic particles or ductile materials. Now, in a typical milling process, if the milling speed is, this is what we have done also. So the question is, in a typical milling process, if the milling speed is increased 4 times, how will it affect the milling time? So the relation between milling time and milling speed, you have to utilize that, and you have to say what will happen to the time if milling speed is increased 4 times. So you have to calculate it using this formula of relationship between the time and this milling speed. So you can calculate T1 by T2 is equal to N2 by N1 raised to power 1 by 2, right? If milling speed is increased 4 times, what will happen to the time? Any answers? So the milling time will be, it will be halved based on the equation, because we have this equation which is relating to the milling time and the milling speed. So we have T1 by T2, which gives us a milling speed N2 by N1 raised to power the 1 by 2, right? So we have T1 by T2, which is equivalent to 2, because the milling speed is 4 times in the second case. So the milling time will be reduced by half. So time will be halved. If you are increasing the milling speed 4 times, the time will be reduced, will be halved. Okay. Now next question is, which of the following is more energy intensive? Attrition, gyratory, hammer mill, or ball mill? Any answers? The answer is attrition mill. Now, this is based on your electrolytic deposition question that you have read in the course. So the question is, under certain conditions during electrolytic synthesis of powders, film deposition occurs because generally what happens during electrolytic deposition, porous powder is formed, right? But in some conditions, it is saying that the film deposition occurs. That is, there is a continuous deposition of the powder, not a porous or a sponge type of a material. So the film deposition occurs instead of a powder deposition. What conditions favor such film deposition? First, low current density, high current density, high metal ion concentration, low temperature. So you just have to think that for a powder deposition, you have a certain conditions. Instead of those conditions, the opposite conditions will be operating so that there is a continuous film deposition occurring on the cathode plate, for example. So what is the combination or which is the right combination for this? If somebody can answer. What should we utilize for such depositions where we want to have a continuous film deposition? We do not want to have a powdery deposition. So for example, for the deposition of for deposition on the powdery conditions, we have normally like high current density is used and low metal ion concentration is used. So for here, because we are using a continuous film deposition, so we will utilize low current and high metal concentration, which is opposite to what it was for the powdery deposits. For powdery deposits, we needed a high current density and a low metal ion concentration. Now, the next question is which of the following technique involves melting of the material? Because we are involved with powder metallurgy. The thermal decomposition, precipitation, hydrometallurgy, or gas atomization. Which of the following involves melting of the material? The thermal decomposition is carried out because of the solid state reductions or solid gas reduction. So there is no involvement of the melting of the material. The precipitation is carried out for a hydrometallurgical process where we have an aqueous medium of the solution in which the oxide or the metal powder is dissolved. So it is also not a melting process. The hydrometallurgy process are the aqueous media processes and they do not require melting. So it is a gas atomization in which the nozzle through which the like the molten material is being poured through is the molten material is because of the melting of the material. So in gas atomization, the material is melted first, and then it is atomized in the form of spherical balls in a gas atomized chamber.
Write it down.
Yeah, it's okay.
Okay, ma'am. Yeah. Thank you.
Okay, okay. Thank you. So that's for all for today. Thank you.
Yeah. Thank you, madam.